right, so we've looked at buffering capacity, and we know that the greater the molarity, the more acid or base my buffered solution can take on. This is going to look at choosing an appropriate buffer if we have more than one buffering solution to choose from. So some of this is going to kind of make sense. That one of the things that we're looking for is obviously a small change in the ratio of acid to conjugate base, or if it was a basic buffer, base to conjugate acid. If I add hydrogen or hydroxide and this ratio barely changes, then my overall pH barely changes. So in a sense, we're looking for like the log of 1, or we want to keep that ratio as close to 1 as possible, as long as my acid and conjugate base or base and conjugate acid were the same molarity, which often they are. So again, like in a sense then, we're kind of looking for a solution where the pH equals the pKa. Then I have a very small change in overall pH when I've added acid or base. Or again, if it's a basic buffer, the pOH should be nearly equivalent to the pKb, opposite log of the Kb. So this might be kind of a good example of a multiple choice question. A, B, C, D. Which of the following solutions will produce a buffering solution with a pH close to 9? Now, first thing you got to ask yourself is, are these buffering solutions? Are they even buffers to start with? Solution A, classic buffer. You've got acetic acid, which is the weak acid. The conjugate base is the acetate ion. It could be any soluble acetate ion, sodium acetate probably being the most common. So far, solution A is a buffer. That's in the running. Solution B, I've got ammonium chloride. Ammonium is the conjugate acid of ammonia, NH3. But then I got what? HCl? Okay, well, HCl is obviously acidic. Ammonium chloride is also a slightly acidic solution. B is out. That thing's not even a buffer. Trick question. C is better. I've got the weak base ammonia and its conjugate acid ammonium. That's a buffer. But D, out. Ammonia is a weak base. Sodium is a spectator. Hydroxide is a base. That's not even a buffered solution. Well, there, we got it down to 2. Between these two, if they want you to pick a buffering solution with a pH close to 9, just think about this. You want the opposite log of the Ka value to be close to 9, since we're talking pH. And they've given me the Ka values, and again, even if this was multiple choice, I could estimate. I bet it's the ammonium. That's probably going to have a pKa closer to 9 than the acetic acid does. So of these two, this one should be my basic buffer, which you might have guessed because we've got a base and it's conjugate acid. The acetic acid is an acidic buffered solution. Now, the other little thing that they could throw at you, what if they had, solution E? Here's one more option. What if in C, these were both, like 5 molar solutions or something like that? Solutions. Or maybe they're 1 molar or something relatively concentrated. And then solution E gives me the same options. And NH3. But what if now these are both, something less. Let's say 1 molar. And now they said, which is the best buffer, which is the best choice for making a buffer solution with a pH close to 9. They'll both give me a pH close to 9, but then the more concentrated solution has a greater buffering capacity. So that might be another little trick they could throw at you. If I had to choose between 2 buffers that both had a pH of 9, the better buffer is the one with the greater concentration. There's one other thing that I kind of wanted to throw at you. There's a multiple choice question, a question in the homework. It's not multiple choice. I lied. This is similar to, it's 45. Similar to 45 in the homework. There's no good example of this in the study guide, but I wanted to kind of mention this. It says explain how to produce a solution. Whoa. I should say a buffered solution. I think that's how it's worded. A buffer solution with a pH of 9. So I don't say explain how you're going to make this solution. So we chose the appropriate buffer. We want the ammonium chloride buffer solution. That should give me the pH of 9. How are you going to make this buffer? By thinking, I don't know. I have no clue, and maybe you don't even care. Let's use the Henderson-Hasselbalch and kind of plug in for what we do know. We want the final pH to be 9. pH is 9. Equals opposite log of the Ka, because this is pH. And I think they gave me the Ka for that ammonium ion. 5.6. Whoa, that's a weird looking 6. 5.6 times 10 to the negative 10th. Here's going to be my variable. Log of I don't know. I don't know what these molarities are, but I do know that it's going to be the conjugate, the ammonium ion, over the neutral particle. In this case, it's the base, NH3. That's my variable. I don't know what molarity, what concentrations should I use. So if we simplify this a little bit, opposite log of this Ka is about 9.25. Ooh, yucky. I can subtract on both sides, and I'm going to get a negative 0.25 equals log of that ratio. Whoopsie. Ammonium over NH3. Ammonia. Okay, so now we can pretend that we are in advanced algebra, a blast from the past, or maybe not so much. And let's solve for this ratio. So if we go 10 to the negative 0.25, that gives me about 0.56. That is this ratio. Concentration of NH4 over concentration of NH3 ammonia. Okay, so now here's where we can explain how to make the solution. They're not going to ask for a specific molarity. I don't know exactly what molarity, but I know that I need a ratio of molarities that would give me 0.56. The easiest way to explain this is maybe to say mix equal volumes. And it's usually, 500 milliliters of each or a liter of each. Let's make this easier on ourselves and say 0.56 molar ammonium chloride. And let's just call the other one 1. Let's say it's 1 molar ammonia. You can use any ratio of molarities that turns out to be 0.56. You could double it, triple it, you could quadruple it, because I get it. The greater the concentration, the better the buffer. But they're not really asking that here. This would give me a buffer with a pH of 9. So there is one like this in the homework. I think it says a pH of 7 or something like that. Then they want you to explain how to make the buffer, and people usually stare at that blankly for a long period of time. We can kind of sub into Henderson-Hasselbalch and solve for that ratio, and you really can put any molarities that would give you that 0.56 ratio.